So, last lesson, I taught you two rules of circuits called the voltage loop rule and the current junction rule. And I've taught this type of stuff for quite a while, and I guarantee amongst you guys, the population of the class, there are probably 6, 7, 8, 10, maybe 12 of you that are saying, yeah, this is awesome, I get it, this is great, I can think of the trucks, and I can think of the gravel, and I can come up with the numbers. And then there's a handful of you in the middle that are getting some right and some wrong. I haven't handed back the work yet, but I can see it when I'm marking it. And then there's a handful of you, maybe 4 or 5, that this just doesn't make any sense. And that's normal, all right? That's normal when it comes to physics, all right? Physics is the type of thing sometimes where we do experiments, we make some observations, and then we try to use that information to explain things. In this case, we're explaining circuits, all right? And I'm getting you to think of two different rules at the same time. And that can be tricky. Today, I'm going to add a third one into it. And so now we're going to have to think of 3 things at the same time. And that's what sometimes becomes tricky. And I'm not going to use the word hard because some people like to say, oh, I hate physics, it's so hard. It's not that it's hard. It's that you've got to train your brain to be able to think of 3, 4 possible rules at the same time to solve a problem that isn't as easy as just putting a number in a calculator. All right? So that means you got to train yourself so that you've got these rules nearby so that you can use the one that you need. Okay. Now, looking at the work that we've done over the past couple of days, I can see that the sheet for the last day, the voltage loop rule and the current junction rule, I've got about half of them done, and the other half still need to be completed. I know the due date was yesterday, but because of the snow day, I'm still giving you an opportunity to ask me some questions maybe after I do my lesson today so that you can get it completed. There may even be time in class for you to complete it, okay? There's also the 2 labs, and I still am missing quite a few labs, all right? I know some of the data wasn't very good. Analyze the data you have, right? I will mark you on your logic and you're making the graphs and finding a slope and doing the calculations. So there's quite a few of those still missing. So we still have some work to do. Okay. So let's talk then about circuit analysis. Now, circuit analysis, we started in on it. Notice we were analyzing circuits the last day. But now we want to put it all together because at each of the resistors, there's a resistance number. There's an ohms. And remember, we know Ohm's law. I'm actually going to put it on the chart paper right now because I haven't done that yet. We're going to write it down on our slide here in a minute as a review. But remember, we studied Ohm's law. And Ohm's law dealt with the resistance. The resistance of a resistor in ohms. And it had a particular equation. Does anybody remember what Ohm's law was, what the equation was? Yep, what do you got? Sorry? V equals IR, but I've already wrote down my R, so could we please give me the representation in terms of this one? Marshall, what do you got? V over I. V over I. Excellent. And just as a reminder, what did we measure V in? Yep. Volts, that's the easy one. You got the easy one. Nice job. Volts. What did we measure I in? Yep. Amps. Very good. And what did we measure R in? Danton? Do you remember? What was that thing that we put there? Oh, I asked you, Danton, because you thought I had asked you the previous one, but sorry, I didn't mean to set you up for that. It'll come to you. It's called Ohm's law. Oh, omega. Yeah, the letter's omega. The letter's omega, and it's ohms. It's ohms. So we do it in ohms. All right. Now, we're going to use this equation a lot today. And I told you a little shortcut for rearranging equations. The math people don't like it when I tell you the shortcut, but that's okay. Some of you need the shortcut, so we're going to do it. So if I'm making a triangle out of this equation, I always think, what goes on the top? What goes on the top? What's going on the top for my little trick here? Yep, V, because it's the top of the fraction, right? V, and then I, and then R, and that gives us our other versions. If I want V, what's V equal to? Yep, IR, I times R, I times R. And if I wanted, what else am I looking for here? I guess if I wanted I, the current, what's it equal to? Yep, V over R, V over R. Excellent. And just because I got red boxes around everything else, I'm going to do the same thing here. Going to do the same thing here. Do the same thing here. Again, I've already indicated to you for our test, which, by the way, is going to be coming up next week, Tuesday, because I will finish our lessons on current electricity on Friday. We will have a review on Monday and the test on Tuesday, all right? I will give you these equations, and you've got to know how to make a triangle out of it, okay? Yep. You mean if you had RI? That makes no difference. It can be flipped around. You're right. Doesn't matter. Yep. Okay. All right. So why did I review this today? Because in the circuits we did the other day, we learned how to calculate the, don't worry about the homework, we just talked about that. Yeah, go ahead, help yourself. We learned how to calculate the voltage in a loop. Please write that down. Voltage loop rule, we already know this. This is what we did the other day. And I've been helping some people out. At lunch, I helped some people out. And I want to make this very simple and not maybe complicated with an equation, but a simple way of thinking it is volts, they add in a loop. The volts add in a loop. What do they add up to? They add up to the total voltage at the power supply. Volts add in a loop. So when you're thinking about volts, you're thinking about loops. Some circuits have one loop, nice and simple. Some circuits have two loops. We can even have three loops. I don't know if we've done any with three different loops. Oh yeah, we did. We've done with three loops. The current junction rule. Remember, a junction is like a side road, if we're thinking about it in terms of driving down a road, right? Again, you'll notice the equation looks the same, but it can be misleading. We need to think in terms of side roads when we do the amps. So I like to write amps, all right? Again, they add, but they don't add in a loop. They add at a junction. Some people aren't sure what we mean by junction. They add up when we hit a side road, all right? They add up when we hit a side road. Now, we looked at some examples that studied the voltage loop rule and the current junction rule separately. That's what your worksheet was the last day. The top part was the voltage ones, the bottom part were the current ones. But we could have put both V's and I's on the same picture. There'd be nothing wrong with that. Then we would know more about the circuit. We would know the current through the circuit, and we would know the voltage at each of the power supplies, or at each of the loads. That teaches us more. If we know V and I at the same place, what could I calculate? If I know I and V for a particular thing, what could I calculate? Yeah, generally, I can calculate the resistance. Which means if I know any of the two things, resistance or voltage or current, I can figure out the third. That's what circuit analysis is. Figuring out V, I, and R at each spot in a circuit. So we are going to add our last rule into this, Ohm's law. And I do like it written as V equals IR. That's an easy way to write it. But because we're going to do lots of quick calculations, I like to put my triangle here. And to be honest, I've done all kinds of complex math in my life, but if I'm doing a circuit analysis, I like to put the triangle in the corner because I want to be able to fire these numbers into a calculator quickly. I don't want to write an equation each time. When you do circuit analysis, this is one of those instances where I don't want to see your work. I just want you to calculate the answer. All right, that's how I know you've done it right. So when written as V equals IR, let's say you were to get an equation that's written like this. The way you fill this into the triangle, because I is beside R, they go in the bottom. That's how you know if you have an equation that looks a little different than a fraction. If they're multiplied, they go in the bottom, and the V goes in the top. Okay? All right. I'm essentially going to do 3 examples for you right now. That's going to be the lesson. I'm going to be done. Then I'm going to give you a worksheet to work on this that I'm going to want collected so I can mark it. There's a second sheet also on there, which is just extra practice. All right? After working for maybe about a half an hour, I'm going to ask you guys to see if you feel whether you know how to do it or not. And I might pair you up with someone who doesn't know how to do it to go through some of the extra practice problems together to see if you can help each other out. I've got some little mini whiteboards. We can even do the work on the mini whiteboards. We'll see how that works out, okay? Let's go through some examples right now. So, here is a classic scenario that is a circuit analysis problem. I've got 2 resistors in series, and you'll notice I've got a little bit of information kind of sprinkled all over it. In this case, I've got a V at the power supply. I've got a current in this position. Notice I don't call it I1. Sometimes I don't, sometimes I do. It doesn't matter. It's the current in that position. And then I've got a resistance over there in that second resistor position. Did you draw my circuit? You need to draw this. This is a participation sport. Yep. Yeah, so just one second. When I give you the assignment or the little practice sheet that I want collected in, the way that I like to put it is V at the top, I second, and then R third. All right? So you will have a V, an I, an R at each position. And some will be blank. And I need you to figure out all of the blank things. So even though I didn't type it in here, here's my V and my I and my R. I'll have a V here, an I here, and an R here. So I got to find those things. And I'm going to have to find the V, and I'm going to have to find the I, and in that one I'm given the R. Okay? All right. So this is fun. This is kind of like problem solving, and we've got 2 rules. We got voltage, and if it's voltage, what kind of a structure am I analyzing? What is the rule? The voltage, yep. In what? In the loop. I can use a voltage loop. Current, junctions. If there's no junctions, they're not leaving anywhere. Resistance, well, for any of these groupings that I'm looking for, if I have 2 numbers there that I've figured out, I can always use this equation to figure out the third. So I'm always going to put this little triangle in the corner. You guys have it on your note up above, so you don't need to rewrite it, but I'm going to write it here, V-I-R. Now, get your calculators ready. Everybody's got to have a calculator nearby and ready to fire it up. Okay. Now I've got to use my rules. This again is where it's like a crossword, except better. No words. I've got a voltage loop rule that the volts have to add up. I've got a current junction rule. See if there's any junctions, get some information. And then I've got that calculation in the corner. Can somebody tell me something true about this circuit in some of the blanks that are here? Can somebody tell me something that's true? what's true at some of these other locations. Yeah, Jess, what do you think? No, you never simply divide by 2. Let me explain. Whenever you're trying to find something, if you have 2 things that you don't know, then you can't do it. So dividing doesn't work, okay? It might be true, but we don't know what the resistance is at the other one, so we can't just divide. So you want to use the loop rule, is what you're doing. And if we were to use the loop rule, we gain 12, we don't know how much we drop off there, and we don't know how much we drop off there. Those are 2 things I don't know. I can't use that rule yet, okay? What could we use that's true? What's going to be true? Yep. Why will I be the same through the entire circuit? You're right. I will be the same through the whole circuit. Yep.
Because you're expecting there's no conjunction.
There's no junctions. There's no side roads. So that one is going to get us the information we need to start with. So if the I is 2 here, what's the I in this position? Yep. 2. 2 amps. Keep coming around here. What's it going to be here? 2 amps. All right. So we use the current rule, no side roads, 2 all the way along. Now you'll notice things are starting to fill in. I now know 2 pieces of information at the start, and I know 2 pieces of information here. Let's go to the start. Let's say I want to find this R. I need to do something with these numbers. What I do is I go to my triangle. I want to find R. What calculation do I have to do to find R at this location, Jay? Nope. I'm looking for R. I'm looking for the R. So put that in your calculator and tell me what R is. I don't need to see the problem written out. Beautiful. It's easy. Well, I guess you don't need the calculator for it. But if you did, it's right there nearby. You see what I'm saying? So notice, I don't want to see the calculation. I have my triangle nearby. I know I need R. I quickly take a look and I know it's V divided by I. You'll notice I have it set up nicely here. This divided by this. And what's the resistance in this position? 6. 6 ohms. Good job. I can do the same over here. I need to find the V. I'm not going to write out the problem. I'm going to cover up that V. What do I have to do to these 2 numbers to get the V? Chloe at the back, what do I have to do to these 2 numbers to get the V? What'd you say? You're saying multiplying? Is that what you're saying? To multiply them? Because you're far away and I can't hear you. Do you know what 2 times 3 is? What is it? I think she said 6. I think she said 6. All right? And that's correct. Now, let's take a look at what we can solve for next. Oh, Jess is now going to throw this back in my face because in the end, it's going to work out the way she said in the first place. But we didn't know at the time. What do you want to say, Jess? You're right, it is 6. But we didn't know that before. Do you see what I'm talking about? You would have been lucky. What's the resistance now? Or let's talk about how she got 6. How did she get 6 there? How did she get 6 there, Travis? Yep. Yep. That's right. You got to drop 6 off at the second one, so you had to drop 6 off at the first one. That's the voltage loop rule. 12 picked up, didn't know 6, so it turned out to be 6. Now we can figure out the last R, cover that up, throw it through the calculator. You're going to tell me an answer? What is it? 3 ohms. 3 ohms. The only reason they're both 6 is because these are both 3 ohms. If they were different numbers, they would drop off different volts. And we don't know that when we start. So we can't use that little divide rule, okay? All right? Because it's not a rule. It's just sometimes it's true. Okay, let's do another one. Don't moan and groan because you're going to have a great big page of them to do. Yeah, we've got to draw them when we do the analysis. On the assignment, it's not drawing. Let me just put in my V, my I, and my R, because I like it in VIR. That's just the way I like to do it. My V, my I, my R. Just hold on, Jess. My V, my I, my R. Those are the things I want to find. V, I, and R. Yes, Jess, what would you like to say?
The triangle thingy,
Yep.
does it matter that the one thing?
The triangle thingies? No, it doesn't. No. That's the proper way to draw a resistor is actually like this. Okay. All right. And I created these pictures. Oh, these are probably 15-year-old PowerPoints that I made. And the easiest way for me to make the squiggly line was to make repetitive triangles. Do you see what I'm talking about? So it looks like some are on the inside and some are on the outside. That's just because of the way I was kind of limited in making that kind of squiggly looking mark. So no, there's nothing important about it. Okay. Looking around the circuit, and this is, again, like I said, it's like crossword, except it's fun because it's math. So we need to think about where to start. Chloe, do you have an idea back there that you want to share? What would you like to share? Where can we start? What can we put?
The ITs stay the same.
The I is going to stay the same. So what's going to be true about all the I's? Yep, they're 5. 5. Oops, look at what I did there. That's wrong. 5, 5, 5. Ooh. Oh, I'm doing it right. 5 and 5. Excellent. Don't be lazy on tests and assignments. Put the units. All right? So when you fill in a piece of paper for me, please put the appropriate units. You didn't do that last time, that's why I'm telling you. Yeah. And if you can't find an ohms, type OHM. Ohm is fine. Jess, are you problem solving here? Are you telling me what to do? Okay, here, let me write my triangle because I like to see the triangle nearby. VIR. What would you like to do, Jess? Because you know you have to do I times R and 5. Sorry, what is the volts on the top?
2, because you have, no.
No.
I thought that was volts at the start. Okay, ignore me.
Okay, ignored. Yeah, Chloe, what am I doing?
10.
Yeah, so volts is I times R, right? We know I and R. That's 10 volts. 10 volts.
I knew that.
Anybody see another location where we can get an information? I don't need to know the calculation. You can tell me the number you got. It doesn't matter to me. Danton, what are you thinking?
The V and I.
Which one? I see V's and I's every. Are we going around the circuit the way we want? Is that what we're doing? So what are you solving for? And what are you getting?
V divided by I.
Ooh, so we're going to get a funny looking number here. So what does that get you? 0.4? 0.4 ohms. So we'll have decimals. That can work. Do you have the next one around the corner? Again, we're doing the same. What is it? 0.2 ohms. What do you want to get next over here at our power supply? What do you want to get next? I can't get the R because I need my equation to get the R, right? We actually could learn, there's another R rule here that I didn't teach you guys. What are we going to do? What are we going to do? Somebody new. What do you think? Yep, what do you got? So add up all the volts, and that's going to be the VT because it's a loop, right? So you can fire it through your calculator. What is that? 10 to 1? 10 to 1? 13? 13 volts? Are you telling me the answer? You've calculated already? What do you got?
I got
2.6 ohms. All right. There's a relationship for the resistors that I didn't teach you guys. In a series circuit, you add them up. But I didn't teach you that rule. Resistance ohms add up in a series circuit. What's the matter, Marshall? 2.6? I believe it's this one. Here, 2. That's a 2? What do we want? We want one of these? Ooh. Is that what we want? We want one of these. We want one of these. Ooh. We're going old school. We're going old school. Put a curve on the top, like Sesame Street 2, right? That's a good old, that's a Sesame Street 2, isn't it? I made it worse? It's three-dimensional. That's my three-dimensional 2. Ooh. Okay, just stop. It looks like a duck. All right. Struggling with my number 2 here. Okay. So, ooh, I just said that on my video. Struggling with my number 2. That could be misconstrued a little bit. Yeah, I just said that. Can't take that one back. So everything's missing. So in other words, I want V, I want I want R. So I've got a series and parallel mixture. I got a whole bunch of exciting things. I'm going to have to use a junction, you're right. V, I, and R, V, I, and R, V, I, and R. And again, notice I don't have numbers. Like, remember in the last one it said V1, V2. It doesn't really matter whether we number them or not. It doesn't make any difference. Okay, we got a junction here, which means we're aware we need to. And what adds up at a junction? Which of our properties adds for the junction? Which of our properties adds for the junction, Jack? The I's or the amps. Either way of thinking of it is the same way. The voltage adds for the loop. The I's add when they split down a junction. Okay. Well, this one's interesting because I don't see anywhere to start with the I's or the V's. So I'm scanning to see if I know two things at a spot. Jay, what do you think? What do you want to do? Up here? What are you solving for? V-I-R. You're right. This screams at me. This is screaming at me. I don't know if you can hear it screaming, but it's saying, you know 2 out of 3 things here. That's what it's saying. And as soon as you know 2 out of 3, you can do that calculation. So what do we have at that spot? What do we have? Marshall, you got a number? What is it? I want I. I want to know what this I is. Marshall, I asked you because I thought you knew. I thought you were going there. Okay. Nice. Marshall, you work great under pressure. Look at, you came up with it, Marshall. You were successful. You did it. Under pressure, you did it. You did it. Yes, he did. V over R, right? V over R. All right? Everybody getting the V over R there? Sorry, covering that wrong one up. Okay, good. Good job, Marshall. Okay. All right, now we can reevaluate. Is there something we can get here? Again, I'm getting feedback from the same people, which means I'm thinking that we're getting it. What's your question?
Since it's
a junction, or a side road.
The side road. Does that mean that the I gets moved? Like, would it be the I be the same on?
It breaks apart. It's like a bunch of trucks. 2 trucks are coming along. Some go down here. Some go down here. Which is, I believe, what Kyla was going to do. And then you said you had a question, and then you answered the question that I was going to ask Kyla for. But hey, no problem. Kyla, what should this I be over here? 0.5. Good work. Nice job. Your friend's taking your answers away from you. Okay, so these are trucks, right? The current is the trucks. 1.5 goes this way, 0.5 goes that way. Excellent. What do we want next? What do we want next? What are you thinking? You're seeing the 2 out of 3. You want to get the V. Good job. Covering up the V. So Jenna, what do you have as an answer here for V? Well, you need to play along. This is a participation sport. Jen is under stress too.
You can't fail in the
It's okay. Here she goes. What is it? 1. You work under the same pressure as Marshall. Marshall's now putting 2 hands up in the air. What's happening? Rachel, you want to get in on the game here? What can we get next? Oh. All right. So, I don't have anything here. Can't do that. I don't have these 2 here, so I can't do that. We've used the junction. There's only one rule left we can only deal with, and that's the voltage rule. And remember, volts deal with loops. Volts deal with loops. All right? Volts deal with loops. If I choose the first loop, I don't know this, I know 6, and I don't know this. In the first loop, I'm missing that V and I'm missing that V. Can't deal with that loop. That loop's no good. I can look at the second loop. Unknown, 6, 1. Danton?
Wait, could you do I, like out of all the I?
Oh, you're right. I could get an I here. Correct. Well, tell me the I. What's the I here? Nope. Nope. I could get the I, but yeah. The I at this position is 2 amps because they split and then they came back together. So the I's came back together. Now, he was looking at the I's. The 2 amps split to 1.5 and 0.5, right? Those are the crux. Then they came along here and came back together at this location to get the current going through there. In terms of the amps, no, you don't add this one to it because this junction split and then it came back together. Okay, so it split and then came back together. What's my next solving? Who am I picking on? I want someone new. I need a V. I need the V at the power supply. I need a loop that's going to tell me the V at the power supply. Ryan, what do you think? What's the voltage at the power supply? 7 volts is correct. Here's where it came from. Ignoring the middle branch. 6 was dropped off, 1 was dropped off, therefore 7 had to be picked up. These 2 are in parallel with each other. So we can get some information here. What can I get there? Jess, are you going to tell me something? What are you going to tell me, Jess?
That the R at front equals 3.5.
You did some math. Nice. 3.5 ohms because she saw 2 out of 3 things. She calculated it up. Yep. This one's 1 because I can now do the last loop, or this is in parallel with that. Correct? Now I can finish this all off and I've got it analyzed. We've got an I times R there. No, wait a minute. R is V over I. Oh, that's a funny number. That's a funny number. Oh, Rachel, what do you got for that number? 6, 7. We'll just go 6, 7. 6, 6, 6, 6, 6, 7. 6, 7. Ohms. Yes, but I'm rounding the second 6 up to a 7, and I'm not going to write all those extra 6s down because we've got to stop at some point. No, we're not doing that. Okay. All right. So that's the end of my video. I'm actually going to stop my video here like I normally do. You guys can go to Google Classroom at this point, and I will be guiding you on what to do.